Today we're going to be checking out 15.7, a section about doing problems involving finding the maximum and minimum values of a function, generally of two variables, so z equals f of x, y. But before we get into the multivariable thing, I just want to quickly recall to your mind how this stuff worked when we were in one dimension, that is, or y was f of x. So recall from Calc 1, really. Finding maximum and minimum values of a function on an interval. Values of y equals f of x on an interval AB. Do you remember how that worked? There's sort of a procedure you go through. One is you take the derivative, because after all it's calculus, and that is you find f prime, well, that'll be a function of x. You set it equal to 0 and solve. So that is, you're going to solve f prime of x equals 0. And you remember with those points where you get that solution, actually we should say something else too. You solve f prime of x equals 0 or undefined. If the derivative doesn't exist at a point, that's possibly a max value or a min value. So f prime of x is 0, or you get some weird error for f prime of x at a particular x value. And those are critical points. Then you're going to, the way I put it is you classify the critical points based on the second derivative. So we have to actually find f double prime too. Don't have enough room to write this. Based on f double prime. I'm just going to squeeze it in there anyway, f prime prime. So then what else do? You also check the endpoints of this interval. All right, so I've poorly planned the board space. Step 4, right under here, I'm not going to write on the wall, be also evaluate f at a and f at b. And if that's, if f of a, for instance, is bigger than it was at any of the critical points where the derivative was 0, then that's the maximum. A piece of terminology people use is that these places where the derivative is 0 are called local maxima or local minima. And then wherever you find the largest of the values, whether at a critical point or whether at the ends of the intervals, that's called a global maximum. Let's do an example. All right, so here's an example. Question asks us to find the local and global. Sometimes, by the way, people say absolute for that same concept, the actually biggest amongst several possibilities. Anyway, the global and the local max and min values of, here's the function, x cubed minus 6x squared plus 9x plus 5. And we're going to work on the interval 0 to 5. Okay. So here's how you go about it. You figure out the derivative, f prime of x, which is 3x squared minus 12x plus 9. Notice that everything in f prime is divisible by 3, so you can factor a 3 out, and you write it as 3 times x squared minus 4x plus 3. And if you've been playing these games for long enough, You probably recognize that as being the product of two binomials. Yeah, that's x minus 1 times x minus 3. Which is easy to check backwards by FOIL ruling this out, and of course you're going to get that. Okay, so what does that tell us? F prime of x is 0. That's what we have to solve for. It means it happens when x is 1 or x is 3. Let me just not write it that way, but probably say add x equals 1 or x equals 3. I don't know why I used or to connect those. It's really and. It's 0 there and there. Yeah, there we go. Okay, so those are our critical points. So we need to check the value of the function at 1, at 3, but also at 0 and 5. Now, there's a second step people usually do. I think I mentioned it. You want to classify these critical points based on whether they're maxima or minima. And for that, I think you need to, well, maybe this is something you've done before, so you'll know. Think about the slope of a function. So I'm going to kind of trace the function, but I want you to pay attention to what slope we're at as we move along. If it has a maximum value, what was just happening to the slopes? Like first I was going up, later I was going down. So if you just keep track of that slope, it went from a positive number to a negative number. That means the slope was getting smaller. Now the second derivative is the change in the slope, right? So what's the second derivative if the first derivative is getting smaller? That's negative. And if you do this all at once, you see that if you go from positive slopes to negative slopes, you get something that's curved in a downward fashion, concave down. Negative derivative means concave down. Sorry, negative second derivative means concave down. And when you're concave down, then that place in the middle where you're horizontal, where your slope is 0, that's a max, isn't it? If you're on a curve like this. And it works just in reverse if your second derivative is positive. Then you might be going from negative values to positive values for the slope. That's having the slopes increase. Second derivative positive. Second derivative positive is curved upward. That spot at the bottom of that thing is a minimum. Okay, so having said all that junk, let's figure out what f double prime is. It is 6x minus 12, and that goes away. So yeah, it's 6x minus 12, which is, let's factor a 6 out of that. That's 6 times x minus 2. So where is f double prime positive and where is it negative? If you're to the right of 2, then x is bigger than 2. And if you're to the left of 2, then x is smaller than 2, and this difference will become negative. So if you laid out the number line, here's 0. We got our critical points at 1 and at 3. And then here's 5. That's the other point we have to deal with. But the sign of f double prime is positive from here to the right. Positive second derivative means it's curved upward, and that makes this guy a min. Negative, f double prime is negative when you're on to the left of 2, and that means this one is a max. So you can actually get a fairly accurate sketch of this graph at this point if you want. You know that it's got a minimum value around 3, so maybe like there, minimum value. It's got a maximum value at 1, so maybe something like this, You know, it was a cubic equation. I've erased it, but it was an x cubed equation. So it's something like this. And then we're actually not using the whole function. We're cutting it off at 5. Actually just above my whiteboard, and at 0. So we're only talking about this portion of the graph. I'm not going to write on my landlord's walls. I have to constantly stop myself from doing that. Yeah, so that's more or less what the function looks like. This was a critical point. This was a critical point. The derivatives are 0 there. You see how if you estimate a tangent line, it's horizontal there. So what was our original function? I gotta remember it now. F of x was x cubed minus, hold on one sec. That's embarrassing. I had to go back and review the earlier part of the film to see what I had used as the function. But there it is, x cubed minus 6x squared plus 9x plus 5. What is our, well, let's just make a table of what our values of that thing are at the various points of interest. Now, 2 of those are critical points, here and here, places where the derivative is 0, right? And then 2 of them are ends of the interval, 0 and 5. So the total number of places we want to get the value of this thing are 0, 1, 3, and 5. Oh, look, odd numbers. Well, not 0. Okay, well, okay. The value of f of x at 0 is quite easy because it's and everything involving x would go away and you just get the 5. What's the value at 1? Also pretty easy because both x cubed, x squared, and x itself are 1 there. So you get 1 minus 6 plus 9 minus 5 plus 9. Oh, wait a minute, that's cool. Minus 5 or plus 5. This is 9 at 1. So that high spot right there is at 9. At 3, what do we get? Let's use a calculator. Actually, the smart thing to do on a thing like this, I'll just illustrate this for you, although I don't know how well you'll be able to see it from the camera angle, but you use the y equals button and go into y equals, kill whatever was there before, put in the formula, which was x to the third minus 6 times x to the second plus 9x plus 5. And then you can use the table method. Hit second and the graph button and you get a table. So at 0 we got 5, at 1 we get 9, at 3 it's 5 again, and at 5 it's 25. So let me give you that information. 5 and 25. So one thing that's wrong with my picture here is that this level and this level are the same. 9 here, this peak, this rounded off peak anyway, is a local maximum. That means local meaning if you're nearby there, you're at the max value. If you go a little to the right, you'll go down. If you go a little to the left, you go down. But you can go down and then head back up. And so you have your global maximum here. We have we have a tie for the global minimum. This one is also a local minimum. That one's only a local max, it's not a global one. And this is it, well, this is actually, since there's a tie, I don't know what to say there. It usually doesn't happen that you get a perfect tie like that. I probably should have just made the interval be one little bit farther out, and then this guy would be the local min. sorry, global min as well. Oh well, I didn't do that, so this is still a global min. Interesting. Well, that's just to remind you of how this all played out in Calc 1. And the things I really want to emphasize are, we took the derivative and solved where is it 0 to find those critical points, like 1 and 3. But we also looked at the boundaries of the interval we were interested in. Now how is that going to work in 3 dimensions, or I don't know, with 2 input variables, when z is a function of x and y? Well, let me sketch for you just sort of an arbitrary function by drawing some contour lines for it. Who knows? I guess that's enough of it. The thing that is going to, so that's sort of a representation of a function. So drawing the various contour levels for it. The thing, though, that is going to correspond to the interval we worked on is going to be some region now. So let me use a different color for that. How about if I had a box that was about like this? And I was interested in figuring out where is the largest and where are the smallest values of this function, whose contour lines we're looking at, inside the box. Well, inside or on the boundary of the box. Okay, so first, what corresponds to the derivative? The derivative when we're in 2D like this is the gradient vector. And there's a couple of spots where it's really geometrically obvious that the gradient vector will be 0. Well, this one at least, it's certainly obvious. Do you see that here? I mean, you're at the peak of a mountain there, right? Or, well, possibly that could be the bottom of a valley too. But anyway, let's think of it as a peak. Is there a direction that you can move from here and go up? No. So the gradient vector tells you the direction you could move to rise, to follow the surface and get higher. And there isn't such a thing here. That's a spot where grad f is a 0 vector. There's no direction that you can move that will see the function increasing there. It's not as clear, probably, but there's also a spot somewhere in the middle of this where that also is true. Grad f is 0. So the reason there's very different looking things here where the gradient is 0 is, well, things get more complicated in 3D. In 3 dimensions, I wish I had some of those Pringles potato chips right now, because that's what we need to visualize. Nah, I don't think I can draw a Pringles chip. I was hopeful, but I'm not sure. Let me try it one more time. Maybe. You guys all know what a Pringles chip looks like. It's got a spot that's horizontal. That is, there's a tangent plane that's horizontal there. It's probably best to think about the shape of a saddle on a horse's back. In one direction it curves this way, in the other direction it curves this way. And there's a point right in the middle. If you just laid your hand on it, your hand would be flat. Well, that's a place where the derivative, the gradient, is 0. The problem is the gradient gives you information about local change, not about a lot of change. So if you're at this location and you walked a ways off from there, you're going to start going uphill. But when you're right at this spot, if you just take one step, you're not going to get any feel of having risen. And it doesn't matter which direction you go. If you go this way far enough, you start to realize you're going downhill. But if you just stay in a little region close to the point where we're considering, you can't detect those changes in elevation. They're infinitesimal. So there's a place here where the ground is level. There's a place there where the ground is level. There's a place here where the ground is level, but that's outside of our region, so we don't even notice that. All right, so I'll tell you from what we've done so far, this spot and this spot, that's where our gradient is 0. We'll figure out how to do this more accurately, not with just a picture soon, but let's get started with that. We've got 2 critical points, in other words. So we would find the value here, we would find the value here. It's pretty clear that that's higher than here. So maybe that one's the max. I guess I should have put some numbers on these contour lines. So suppose this one that's sort of outside of everything was level 0. This is level 1. That loop is 2. I guess this one is also 2. This is 3. I guess that value is around, I don't know, 3.5 or something. This spot is a little bit less than 2, but a little more than 1. So I'll have a 1.5 or something. But where's the highest place in this box that we've been talking about? The region that over which we're trying to find the maximum. It's actually over here somewhere. In fact, there's a spot somewhere here along the boundary where we're almost at 4. That's a level contour for 4, which is much higher than the 3.5 that's there. And it turns out, by the way, our state, Connecticut, has this exact feature. There's a mountain in Connecticut called Bear Mountain. So this could be Bear Mountain. It's way up in the northwest corner of the state. And they call it the highest peak in Connecticut. But it is not the highest point in Connecticut, because there's a mountain whose peak is in Massachusetts, and the border of Connecticut, well, this doesn't look geographically right now, but the border of Connecticut runs right along the side of that mountain, pretty close to its peak. The peak's actually in Mass, but this location along the border is your highest spot in Connecticut. Where's the lowest spot? Is it this critical point? Nah. There's values here that are down somewhere between 0 and 1. So we would get a spot somewhere in there that's even lower, or maybe it's over here. So there's going to be issues figuring out where these spots that I've kind of drawn nebulously, because I'm not quite sure where they are, but there's a maximum that appears on the boundary, there's a couple of minima that appear on the boundary, there's a thing that turns out to neither be a max nor a min, and there's a place where we're at a local max, but it's not the global, which happens over here. All right, so how do we go about actually locating this kind of stuff? There's a procedure you follow to find the local maxima and minima. And then there's a whole other method. We've got another chapter to go on optimization problems like this that lets you work on the boundary. So right now we're just going to find and categorize local max and mins. There's a way to refer to max and mins at the same time. So I'm going to introduce that word right now. If you didn't run into this in Calc 1. Extrema, places where the value is either a maximum or a minimum. It's an extreme value, so we call it an extrema. If there's one of them, it's an extremum. Like maximum is one high spot, and maxima is a fancy car. No, I'm kidding. It's a pluralization that comes from the Latin roots of these words. Okay, find and categorize local extrema. So the setup is you've got z as a function of x and y. And you probably have some closed region that the whole thing is done on. But for right now, we're not going to worry about that. We'll just think about finding all the critical points. So first, you are going to find the gradient vector for that f. That will be a function of x and y. And the next thing we're going to do is solve for the locations x and y coordinates where the gradient vector is 0. All right. Those are going to give you a short list of places where there's literally no direction that you can go, which will either increase nor decrease the function. What do we do for the second derivative? Well, we have some things that act like second derivatives. We have the second derivative in the x direction, which is f sub x x. We have the second derivative in the y direction, f sub y y. And we have the second derivative where you do it first in the x and then in the y. I don't think I proved this to you, but I tried to show it once or twice that if you do this in the other order, f's y's x derivative, that these two come out the same. It's a funny fact, all right? Now, it turns out there's a way to combine these things together to get a number that works just like the second derivative test did in Calc 2. But that requires a slight explanation. So for right now, I'm just going to tell you that thing, and then I'll give you the explanation in a second. You calculate this number, they call it h. It's the product of fxx and yy minus the square of fxy. Okay, and here's what happens. If that number is positive, so if you've got a positive number for that thing, that's called the Hessian, but if it's positive, then you're either at a max or a min. You still don't know which. But if it's negative, you're at a saddle point, the place where it's neither a max nor a min, like the spot in between two mountains that I showed in the last contour plot thing. So if h is greater than 0, you're at a max or a min. If h is negative, that tells you you're at a saddle point. And if h is 0, you can't tell. Just like when the second derivative test, if you got 0 for the second derivative test at one of your critical points, it's just inconclusive. So I don't quite have room to write h equals 0 implies it's inconclusive, but this is a bit like the second derivative test. So let's get into explaining where this h comes from, and how do you actually tell the difference between a max or a min. I'm gonna give you a notion to think about, which is not quite the same as h, but it's very similar. It's known as Gaussian curvature. And what Gaussian curvature is, more or less, is this. If you have in the x direction, you're curved upward, and in the y direction, let me draw that foreshortened, you're curved upward. So that was going in x, and this was going in y. If you're curved upward in both directions, your Gaussian curve, these was positively curved in x, positively curved in y. That turns out to be saying something like this: f sub x, x is greater than 0, and f sub y, y is greater than 0. What the Gaussian curvature is the product of these two curvatures, more or less. Really what you have to do is figure out which has the greatest curvature upward, and what direction gives you the least curvature upward. So max and min of the upward curvature. and you multiply those things. But still, if one's positive and the other's positive, it's going to come out positive. So this is a positively curved surface. Now, here's the problem with Gaussian curvature. It can't tell whether you're at, do you see that this thing I've drawn is sort of like the bottom of the sphere? You know, you've got a curve upward in one direction, upward in the other direction. You're at the low spot on a bowl. Like a friend of mine currently is stationed at the South Pole in Antarctica, and she's there. That's positively curved, positively curved. The product is positive. Well, what if we had negative curvature? If it was a upside down bowl, it would look like that with, wow, that was a terrible drawing. Let me try that again. What does a bowl look like after all? That way and this way. So there's a spot there at the top of that bowl. And if you look at here, you've got negative curvature in the x direction. Something like f sub x is negative. And in the y direction, also negative. But the product of a negative and a negative is positive again. So this is also a positively curved surface, even though it's exactly in the opposite direction of the first one. This guy would have a max at the top. This one would have a min at the top. What do you get? How do you get negatively curved surfaces then? Well, that's when the product of the curvatures is negative. And that happens in this Pringle chip or saddle kind of configuration. So if in one direction we curve upward and in the other direction we curve downward, I don't know if that looks like a saddle to you or not. I think it doesn't. I'm really having a bad time trying to draw saddles. Anyway, one direction's curved upward, the other direction curved downward. The product now is a negative number. So that sort of thing, a saddle surface is a negatively curved surface. All right, so what if you have one of these two choices, either I've erased the other one, but the upward opening bowl, like that, where you've got a positive curvature in both directions, so you get positive for the product. Here we've got negative curvature in both of them, so we get positive for the product. These are the two things. How can you tell them apart? Well, this guy had both derivatives, both fx and fy were negative. This guy had both fx and f double x, I should say, and f double y. Those were both positive. So here's what you do. You figure out that h I showed you a second ago, and that distinguishes whether you're in this kind or in this kind. If you're in the saddle shape, h is negative, you don't have to do anything. It's neither a max nor a min. If you do get a positive h, figure out which of these cases you're in, because you're going to be in one of them. And people usually just say, look at f sub double x. If f sub double x is positive, you'll be at a min. If x sub double x is negative, you'll be at a max. Now, if it's easier, go ahead and look at f sub double y, because the point here is that both of them have the same sign. They're either both positive or both negative, and we only care about what that sign is. Are they positive or are they negative? But that's what we normally do. So let me spell this all out. I've tried to sketch what was going on. Let's make it concrete. I'll give you a process to go through to figure out whether you're in a max or a min or a saddle point. So that I guess I would call this the multivariable version of the second derivative test. Oh, shoot, I just remembered. I had promised to tell you where H came from, so I want to do that before we pass on. What H actually is a determinant of a little matrix, so that's 2 by 2. The matrix has f sub x, f sub x, f sub y, f sub y, and then this one is x, x, and this one is y, y. Okay. I just had to remember what order to put the variables in. It doesn't matter. It's a table of all the second derivatives. That's what it is. F sub xx in the upper left, f sub yy in the bottom right, and the two things that are sort of off diagonal from each other, those are what are called the mixed partials. One is take the x derivative and then take the y derivative of that, and the other it's vice versa. But these two guys are equal. Well, the determinant, which is what we mean by putting that absolute values around there, it's just like that little calculation we do in cross products. You multiply this way with a plus sign, you multiply this way with a minus sign, and you subtract. So this is f sub xx times f sub yy minus f sub xy times f sub yx. But those guys are equal. So you can re-express this whole thing, this so-called Hessian determinant, as the product of the double x with the double y minus the square of the mixed one. Use that one. So that's what this thing is, how you calculate this thing. That's why it's what it is. It's the determinant of a particular matrix. Okay. Broken the matrix while I was doing that. And I still have, I said it, but I didn't write it down, so I think I better do this. This is called the Hessian determinant. The matrix right there, that little 2 by 2 matrix, is the Hessian, and so we're taking the determinant of it. That's why it's called that. So, do I have enough space to say what to do? I think not. So I'm gonna take this part away. We'll write it again. So don't forget. You'll write that Hessian determinant thing enough times in doing problems that you will get quite used to it and memorize it by accident. But here's how the second derivative test rolls. You first calculate h. I'll write it again one more time. F sub double x times f sub double y minus the square of the mixed partial. F sub xy. You check the sign of that. And by the way, that's a good way to say it. You don't care what the value of it is. You just care whether it's positive or negative. So a lot of times you can figure out whether it's positive or negative without ever having figured out what exactly it is. So you check the sign of h. And if h is negative, you're at a saddle point. So that will not be a max or a min. If h is positive, you're at a max or a min. And then you're going to have to do something else. The something else is to now check the sign of fxx. And again, you don't have to calculate what fxx is. You don't have to get a value for it. Just need to know whether it's positive or negative. So at this stage, I would stop here, right? If I find out a saddle point, let's put like a stop sign there. Say stop. But if we get h is positive, we're at a max or a min, we have to go on to this third stage, which is to check the sign of f double x. If f sub xx is positive, that's upward curving, but that means the value there is a negative. The value there is a minimum. And if it's vice versa, f sub xx is negative, that's going to tell you you're at a max. So it's a good bit more complicated than just checking the second derivative. This Hessian determinant behaves kind of like the second derivative, but also because we're in the world of surfaces, there's more than one way you can be curved. In ordinary graphs, they were the concave up or concave down, but here they can be a combination. One way concave up, the other concave down, or they can be going in the same direction. And when they're in the same direction, it can go either together, downward, or together, upward. Quite a lot. All right, so that's the multivariable version of the second derivative test. I guess we better put this thing in action, huh? I'm gonna pick a function just randomly out of the textbook. This is problem 15 in the book. 3x squared plus 3y minus y cubed. What was that again? 15. 3x squared plus 3y minus y cubed. One more time before I lose it. 3y minus y cubed. Yeah, I keep doing it wrong. All right, there we go. I don't know why I would care so much about what it is, because it's just an example. We're going to be able to work it out for that example whenever I end up writing down. If I'd made an error in that, it wouldn't matter. But okay, so this is a f of xy situation. So the first step, remember, it's sort of like the find the derivative and set it equal to 0, except the derivative now will be a gradient vector, and we'll set it equal to the 0 vector. Some people just like to say, get the x partial and the y partial and set them equal to 0, which is a fine way to do it too. Let's stick with what I said originally. Figure out what grad f is. The x partial of this guy is going to be 6x, and those guys are treated as constants, so they go to 0. So you get 6x there. And the y derivative is going to be 0 plus 3 minus 3y squared. So to say that grad f is equal to the 0 vector is to say that 6x equals 0 and 3 minus 3y squared equals 0. Now, what do these two tell us? Well, if 6x equals 0, then x equals 0. But here we get something else. We get, really, can you just see that y squared would have to be 1? 3 minus 3 times 1 would give us 0. So if y squared was 1, you've got a solution. But if y squared is 1, that means y is either plus or minus 1. So if you plot this in the xy plane, we're going to look for things that have an x coordinate of 0 and a y coordinate of either plus 1 or minus 1. Here and here. So that would be 0, 1, and that would be 0, minus 1. So the problem actually in the book just said, figure out where the critical points are. And so as far as that problem is concerned, we're done. That's all you have to do. But I'd like to take it one step farther and do the second derivative stuff with this. Figure out whether these are maxes or mins or saddles or whatever. All right, so I just don't want to erase the original function. Let me recopy grad f here. The feeling we're going to need it. I could be wrong about that, but let's do that, and then I can erase. Will we remember where those critical points are? I think that was simple enough. I'll remember that. So what I'm going to need now is the stuff to calculate the h, the Hessian determinant. H, remember it's fxx times fyy minus the square of fxy. So we'll need that. Well, the second derivative of x with respect to x is take the first derivative and take one more derivative of it with respect to x. So you get 6. What's f sub y, y? Let's take one more y derivative of that guy. That one will go away and we'll have minus 6y. And then if I take the x derivative and then take the y derivative of that, I'll get 0 because 6x is just a function of x. It doesn't have any y dependency in it. And similarly, if I take the y derivative and then take the x derivative of that, I will get 0 as well. So this is 0 squared. Let's simplify this. This is equal to negative 36y. Right. So when I look at my two critical points, this one and this one, here the y coordinate is positive and h is going to be negative. Here at this other spot, the y coordinate is negative, and we'll have a negative times a negative. Here h is going to be positive. So what does that tell us? When h is negative, this guy is a saddle. When h is positive, I don't know which it is yet, but we've got a max or a min. So to finally figure out whether it's a max or a min, we check the sign of f double x. Well, that was in here. Yeah, right there. It's a 6. So since f double x is also positive, that means in the x direction we're curved upward. Oh, and we're at a min. There's the whole process. So this surface, if we knew what it looked like, I don't know exactly what it looks like, but I know right down here we've got a minimum value, and right down here we've got a mountain pass, a place where it's curved upward in one direction and downward in the other. That was fun. There's some more stuff in this section about working out what happens along boundaries of surfaces. Boundaries of the regions that we might be working on. If the boundaries are simple enough, then we can just sort of translate into a Calc 1 problem. So let me just give you an example of this. Suppose we've got some function like this, with contours that are concentric ellipses. And I've got a region that's like so. And I'm trying to find a maximum value. I can tell you just from the geometry of it that it's somewhere in here. Well, what we are going to do is say, see, this is a vertical line. That means its equation is something like x equals a constant. Well, we can think about traveling along that line and composing our position vector along that line with the function we're dealing with. So we'd have something like f of xy kind of getting turned into f of whatever the constant is, comma y. So if k is really a constant, this thing ends up just turning into a one variable problem. That is really, that thing, that expression is just f of y. K is a constant, it doesn't really, you don't put it in the argument list if it's a fixed number. And we know how to take the derivative of that and find where we've got maxes and mins and do all the stuff that we did in Calc 1. So locating this point, if the boundary is something nice like a straight line, not so hard. The trouble comes in when the boundary is more exciting. What if it's a line at an angle, or what if it's curvy? And for that, there's a whole another section to go about finding maximum and minimum along the boundaries of regions, called constrained optimization. And that's what we'll be doing next, I think. Great. Yep. 15.8, it's called the method of Lagrange multipliers. Lagrange is this rather famous French mathematician from around the French Revolution era. I think it was a little bit earlier than that, so he's kind of an old guy during the Revolution, but anyway, pretty important mathematician. Napoleon was very fond of him. He called him his mathematician. Lagrange, anyway, Lagrange multipliers is next, and we'll leave that here. Have a good, let's see, hopefully I'm posting this relatively shortly, so you'll be watching it either Thursday night or Friday morning, and we'll see you in class. Ciao.